In the previous video, we set up a relationship of what heat is as it compares to the mass, the specific heat, and the change in temperature. And here we're going to go through an example of this. So 1.00 kilograms of magnesium at 40 degrees Celsius is added to 1.00 liter of water at 20 degrees Celsius in an insulated container. What is the final temperature of the magnesium water mixture? And in this, we need to know that the density of water is 1.00 grams per milliliter, and the specific heat of magnesium is 1.02 joules per gram degree Celsius, while the specific heat of water is 4.18 joules per gram degree Celsius. So essentially, what we're going to do in this particular problem is we have a vessel of water, and we have 1.00 liters of this water, and it's at 20 degrees Celsius. And what we're going to do is we're going to take this block of magnesium, which is going to be 1,000 grams, and it's at 40 degrees Celsius. We're then going to place this block of magnesium into the water, and we're going to have our vessel, which contains our water, and then there's going to be a block of magnesium in it. The question is, what is the final temperature of this mixture? And we need to use some principles from the first law of thermodynamics, saying that our heat lost by the magnesium is going to equal the heat gained by the water. So we can say the heat loss, which would be a negative Q of magnesium, is going to equal positive Q for the water. Okay? And remember, when we're talking about energy or we're talking about heat, the sign is going to indicate a direction, telling us whether we're losing heat or we're gaining heat. So remember that Q is equal to the mass times specific heat times the change in temperature. So the mass of our magnesium is 1 kilogram or 1,000 grams times the specific heat of the magnesium, which was given in the problem as 1.02 joules per gram degree Celsius, times our change in temperature, which will be the T final, which is what we're solving for, minus our initial temperature, which is 40 degrees Celsius. This is going to equal the Q of the water, which is the mass of the water, times the specific heat of the water, times the change in temperature. So that's going to be equal to positive 1,000 grams of H2O times the specific heat of water, which is 4.18 joules per gram degree Celsius, times the change in temperature, which will be the TF minus the TI, and our initial temperature of the water is 20 degrees Celsius. So we can now go through and we can solve for our final temperature. And we're going to need to use a little bit of algebra to do so. 1,000 times 1.02 is 1020 joules per degree Celsius, because our grams are going to cancel out, times TF minus 40 degrees C. That's going to equal 1,000 times 4.18, or 4,180 joules per degree Celsius. And again, our grams cancel out here, times TF minus 20 degrees C. If we can rearrange each of these, we can say that 1020 joules per degree Celsius times TF minus 40,800 joules is going to equal 4,180 joules per degree Celsius times TF minus 83,600 joules. If we rearrange each of these to get the final temperature on each side, and I'm forgetting a negative sign over here over on the left, we can subtract 4180 from each side to get negative 5,200 joules per degree Celsius times TF is going to equal, and we're going to add the 40,800 joules to the 83,600 joules to get 124,400 joules. And if we go through and divide and solve for TF, we're going to get 23.9 degrees Celsius. And this is going to be the final temperature of our mixture. And note that even though we started with a metal at 40 degrees Celsius, we ended up with a temperature that's much closer to the water, because the water has a much larger specific heat than the magnesium does. So in these particular problems, we can ask for a mass, a specific heat, or any part of the change in temperature when we take one metal object and place it in some kind of beaker of water. And this is the process that you would use in order to solve this.